Next up, we have Dr. Kit Kennedy of Starfish Space presenting Enabling Smart Spacecraft Using New Compute and Software. Kit, it's all yours.
Okay, great. And I guess the, okay, looks like the slides are coming up. Okay, yeah, nice to meet you all. I'm Kit. Glad to be talking to you a little bit today about smart spacecraft. So I'm kind of talking about going towards a new mental model for deploying compute and software in space. A couple disclaimers here just to start are that I'm not a kind of a deep flight software engineer. I kind of exist between at the intersection point of flight software, GNC, and systems. And so you know, that's good context. And then also another thing is that this presentation is kind of given from the context of a space startup and what kind of we've discovered is important and like how we I don't know, some of the perspective that we can provide in the situation. So useful context going forward. One thing I also realized is that I did not put a slide in here introducing our organization, our company. So, you know, startup life. But some notes on us. We were founded by former Blue Origin GNC engineers in 2019. We're based in Kent, Washington, so near Blue Origin. We're almost 20 people now. And kind of our big mission that we're working towards is we're building Otter. So it's like an animal, Otter. We have a marine theme going on. And the main mission for that is both GEO satellite servicing and LEO debris removal. So we've kind of explicitly designed Otter from the ground up to be useful for multiple use cases. And we're kind of working with customers on further development for both of those use cases. And that's kind of where we see a lot of the value of Otter as a product, that it can scale to more missions and kind of just scale faster because we designed for multiple missions from the start. We raised $7 million last year in a seed round, and then also we got $1.7 million from the Space Force for an SBIR for work on our autonomous software for satellite proximity operations and docking. And I should say that GNC is kind of our bread and butter here. Could you go to the next slide, please? So what I'm talking about here is kind of the claim that we need a more flexible mental model for developing and deploying space flight software. Core flight software needs can, at least for certain use cases, often be handled off the shelf. You know, there are examples of frameworks that solve this problem, like CFS, CubeOS, et cetera. And from our perspective, if we can use those as kind of something to build on, then we don't have to reinvent the wheel with building our own critical flight software. And kind of another perspective on this is that there's lots of exciting capabilities that are coming online from the terrestrial compute and software side. And keeping an extreme bifurcation between terrestrial and flight software, we think that kind of slows things down. And particularly for us as a company, there's a lot of kind of terrestrial compute and software that we want to be able to leverage. So our perspective on it is that if we can embrace more kind of modular hardware and software frameworks, it could move us and the community faster. Next slide, please. So maybe a good analogy for this is thinking of satellites as smartphones. So smartphones have core capabilities like making a phone call. And then there's many apps that run on top of that. And I don't know about you, but I've definitely run into plenty of apps that will freeze and just stop working and you have to just kill the app. But the smartphone keeps working. Not saying that we actually want to have that happen with our flight software, our GNC software in particular, but it still is, it's useful to think of this kind of separation between core capabilities, the things that absolutely have to work all the time or we're going to break the spacecraft, and things that might not be, that are less critical. So core capabilities are like command and telemetry, basic attitude and thrust control, et cetera. And then we can think of ourselves kind of as an app. So we're running our GNC autonomy software, but it doesn't have to manage those core capabilities and doesn't actually have to respond to things with maybe with real-time requirements. Some other examples of that are like payload tasking, payload processing, et cetera. Can you go to the next slide, please? I wanted to give a little bit of perspective of the growth of space compute power here. Note that this is definitely not a comprehensive review. This is just me putting a few points on a plot to kind of illustrate a point. The y-axis here is compute speed in mega instructions per second, and then the x-axis is years. So just kind of looking at things, we started off with very low compute capability. So Apollo guidance computer, about 40 millimips. And then things, looks like every 10 years or so, have advanced by an order of magnitude in power. And then I added a couple points at the end of this curve here that are the Raspberry Pi 3 B+ and the NVIDIA Jetson Nano, which are basically hobbyist hardware for that people use to run embedded systems in their home or something like that. However, I do know for a fact that Raspberry Pi 3s have been launched into space, and these things completely blow previous generations out of the water in terms of compute capability. I mean, that's a little bit unfair because they don't have the same requirements in terms of rad hard, but it is kind of interesting to think about the fact that like we can do a lot with hobbyist hardware these days, and you can run some pretty compute intensive algorithms on them. And if we could leverage that ability to just run some of the latest terrestrial hardware, that could help us a lot. Granted, with perhaps more risk. Could you go to the next slide, please? So just kind of going down the rabbit hole here to think about some of the terrestrial applications that are so interesting. Just kind of defining edge compute. I would say this is real-time processing of data on a device, or the hardware that does the real-time processing of data on the device, where the data is collected, rather than sending it to the cloud for further processing over there. So this is essentially making things smarter at every individual node that you might deploy out in the field. A lot of this has enabled many computer vision applications where you couldn't run them before because you just didn't have the connectivity. This hardware often features GPUs for running advanced machine learning algorithms, neural nets and the like, and it enables some pretty incredible capabilities. Next slide, please. So some of the example applications of modern edge compute are here. So object detection, drawing bounding boxes around detected objects in an image, pose tracking, figuring out the attitude of something and maybe subcomponents of that thing. Semantic segmentation, classifying different parts of an image as different things, and also anomaly detection, just looking at signals in real time or not quite real time and looking for anything that's amiss. So these are applications that are very useful, particularly for us thinking as a rendezvous and proximity operations and docking centric company. That if we can use some of the latest terrestrial algorithms and machine learning, neural nets, et cetera, and we can run those in space, perhaps on a payload processor, and kind of use the latest and greatest there, it's super useful for us because that helps us with identifying the target that we're trying to dock with, characterizing that target, estimating its pose, estimating if something is spinning or not, et cetera. Also, anomaly detection is always very useful. Next slide. So just kind of thinking, so that's kind of a call to action there. Like, what could we do with some of the latest and greatest in the terrestrial realm? Thinking about some of the adoption challenges. Why isn't satellite software like smartphone software? So this is kind of just thinking about different things here. Whether, things that are very justified from kind of the history of developing flight software, but things that might, at least in some use cases, hold us back. So number one is inertia. So maturity, heritage of older code and approaches. If it ain't broke, don't fix it. Two is systemic coupling. All code is treated as flight critical. Three is the desire for complete understanding of the code base. I know I've been on projects before, space projects, where no external libraries were allowed if they hadn't been fully vetted. Somebody had come through them with a fine-toothed comb, and that's definitely not how the wider tech and software world, particularly software startups, work. And number four is the lack of network effects for kind of adapting terrestrial code within the space community. So I think that obviously I don't have the answer for all of these things right now. And this is just me agitating a little bit, but I think there's useful things we can do to kind of to approach some of this. The next slide, please. So from our perspective, a useful solution here is systemic decoupling. So using modular architectures. There's one that a lot of attendees at the workshop will be very aware of, which is kind of abstracting out some of the basic flight software capabilities using something like CFS. And there's some other kind of open source solutions for that, like CubeOS and ROS, which, as we just heard a couple of presentations ago, there's considerations when you want to use ROS in space. And then there's also, and you can kind of create an app layer like that. So you have the core capabilities, and you can build your smart mission apps on top of that. There's also hardware enforced modularity. So using a main flight computer that is where your critical code runs, and that flight computer should not go down or should be very dependable. And then running things on a payload computer, a separate payload computer that, say, if it were to power cycle, it wouldn't be such a big deal. So we think that kind of using these two, like thinking about these as kind of as ways of putting in modularity, can really kind of help speed up the development process. Next slide, please. Why now? So why is this kind of important to think about right now? So there are a few push factors and pull factors that I've identified here. First of all, terrestrial edge compute is rapidly maturing. There's been a recent proliferation of AI, data processing, robotics, software frameworks, and that's stuff that would all be very useful to use. Interestingly, there's also kind of a new space hardware supplier community that is coming online that facilitates modular decoupled design. And we've had the benefit of being able to kind of work hand in hand with some of these suppliers. And then also there's new space software frameworks that are designed to be modular from the ground up, as I mentioned on the previous slide. So those are things that kind of enable us to do this, and that could potential benefits here. But why are we pulled toward those things? Why do we actually want to integrate those things into our processes? Well, there's more capital and people power coming online for exciting new space projects, particularly in the startup community. So there's just a lot more kind of people entering into the field that I think we can maybe move things a bit faster if we can use some more like agile development processes. And there's also new organizational approaches to space technology development. For example, NASA's COTS program, Commercial Orbital Transportation System Services. So I think that these things together mean that we're kind of at an interesting turning point in terms of the history of developing space flight software and also space hardware. Yeah, and next slide, please. I put this in here a little bit tongue-in-cheek, I'll admit, but we use a lot of Python here at Starfish Space, and we found a lot of benefit from it. And so I just kind of wanted to call out here with my little love letter to Python, how it's been beneficial for us as a company. So first off, writing in it is just plain fun. It's interpreted, so I find it easier to debug. It's an emphasis on readability. There's useful features like list comprehensions, code introspection, that might exist in other languages in various forms, but I know and love them in Python. There's a huge community, lots of packages, lots of stackoverflow.com answers, and that is not something to discount, to be honest. The ability to just look up a question that you have and find almost a recipe that's available on Stack Overflow can be very useful. There's also big communities for data science, robotics, machine learning, deep learning development, both on the research side and the commercial side. They're very mature frameworks that kind of grew within Python natively. Next slide. And I just kind of wanted to think about some of the showstoppers that traditionally mean that Python is not relied on as flight software usually. First off, there's the limited performance question. So obviously Python is not real time. You're not going to be running it on a real-time operating system and expect to meet real-time requirements. And also it's slow because it's interpreted. But there are libraries you can use that can speed things up a lot, like NumPy, SciPy, et cetera, that are often just wrappers around compiled C code. You can always rewrite bottlenecks in C. And we've definitely encountered this times and we were able to kind of isolate the blast radius of the code that we needed to convert over. And you can't run it on a tiny micro necessarily. There are approaches for that. But do you really need to? One of the arguments I'm making here is that by separating out some of the capabilities to a payload computer, having hardware modularity, you don't necessarily need to run this in that way. Unmaintainable. I've found that type hints in Python and linting those type hints go a long way. Type hints are essentially, they look like you're typing your variables, but they're not actually used for a static typing system. It's essentially just adding readability to your code. But I've definitely found in the past few years of working with Python that it really helps a lot with understanding code when you go back and look at it a few years later. And I think this can actually make Python in some cases easier to maintain just because it's easier to deal with the actual code. And then in terms of unreliability, I feel like there is kind of a notion that Python is unreliable, but it's used widely in industry and in space for hardware in the loop testing, ground stations, et cetera. I mean, I've used it for those things. So I think it would be unfair to characterize it as unreliable. Next slide, please. So why is Starfish Space interested in a new approach to flight software development, or at least an approach that we see from our perspective? So we plan to perform complex missions with our Otter space tug. There's a rendering of it there on the right. And for us, a modular hardware software approach has really helped us move a lot faster. And we have code on orbit now that we're testing that we've been able to kind of move through the steps of deploying that and updating it a lot faster because of this modularity, and being able to rely on kind of some of the lower level core functionality that we didn't have to re-implement from scratch. And we envision a future of complex autonomous robots on orbit, and we think that this will help develop that ecosystem, move things along faster, so that we can the space startup community as well as the existing space community can do more interesting things faster. Next slide, please. So in summary, from our perspective, at least for certain use cases, the current model for developing flight software is too rigid. We don't think it all has to be flight critical. We can rely on some existing solutions that are out there, at least for certain use cases. And by doing this, by having kind of a new approach to modularity, we can exploit a lot of the existing terrestrial compute and software capabilities that are out there. So kind of the proposed way to get there is, and obviously this is already ongoing, but just encouraging adoption of space-specific software and hardware frameworks that promote modularity and decoupling, and deliberately trying to use the latest and greatest terrestrial compute and software for space applications. We certainly are. Next slide. I think that's my final one. So thank you for your time today.
All right, thank you. We do have a couple of questions going to go into. So first one up, why not use an ARINC 653 RTOS to partition the flight critical software from the COTS software for the issue of systemic decoupling that you mentioned?
Good question. And that is, I mean, that's a possibility. To be honest, like some of this modularity was a result of kind of the way we were able to procure hardware from providers, from our providers for the satellite we're building. And so I wouldn't say we necessarily stumbled into it, but we did end up with more modularity than maybe we would have started thinking about, and maybe we would have considered something like an RTOS on a computer that enables us to kind of divide out areas of responsibility. But I do think we found in the process that there's been a lot of benefit to just us having to not worry at all about any of the stability of the computer that we're running on. I mean, the software that we're developing in some cases could just have a bug and just go down, and the satellite would still be fine, and our GNC software could be brought up. We benefit from the fact that a GNC time constant is pretty long, as opposed to software drivers that need to get new data from hardware devices. But yeah, we could go down fully and be brought up and be perfectly fine. So hopefully that answers your question.
All right. With a radiation-hardened core computer and a softer payload computer, would having multiple payload computers working in parallel allow for issues to be corrected and still allow using modern hardware?
Yeah, no, I think that's a very valid point. And that's something that we thought about a little bit, and I think we're going to need to move more towards in the future. Obviously, we're not going to just be doing things in low Earth orbit where we can benefit from the bulk of the Earth's magnetic field. But yeah, that's an approach that we're looking at and definitely considering. And I think that does provide the ability to use some of the latest hardware and even be flexible about which hardware it is, and be able to upgrade it over time, and not pay the cost of having to have everything be totally rad hard and totally totally reliable 100%.
Okay. Next question. With the inclusion of external libraries, are there concerns with security? The left pad debacle also comes to mind. It'd be scary to lose a dependency in your build process for equipment that's already in flight.
Yes, that is a good point. And I should say that we are a startup and we are refining our processes a little bit here. We don't want to just open the floodgates entirely, that any package that crosses somebody's mind at 11 o'clock at night while they're trying to solve a very niche problem in our software, that just automatically gets added to the include list of the packages that we'll deploy on orbit. But we do want to be a little bit more open to using at least some of the packages out there that can solve some key problems for us. I'm speaking in generalities there, but there are a lot of Python packages that are very useful. And some of that, in some of those, it's very hard to be able to comb through all of it. So it's a little bit of a process refinement still, but we're at least kind of erring on the side that having the ability to include more packages helps us develop faster.
Okay, and time for a few more questions. Got one more here. On the 2 ESA flight software projects I've been involved in, it was frowned upon to use external libraries unless it's the absolute basics. So we had to create our own mini library to get the algorithmic work going. I can imagine usage of Python needing a whole new set of standards, restrictions, Mr. Equivalent checks, etc. At this point, the question is, would it be worth it?
That's fair. And of course, that kind of speaks to my second disclaimer, that we're a startup, and so we exist in a different context, and there's some requirements that we don't have that I know many of the attendees of the workshop do have. So that sounds a little bit like a cop-out, but I mean, obviously, as we mature, there will be more requirements that we have to meet, and we do have an eye towards the fact that we are going to be working with very expensive satellites, and we need to be aware of some of the requirements that are going to be added to us. But I do think that at least kind of getting started and moving towards a minimum viable product of a satellite that works in space, and demonstrating that, we've been able to make a lot of progress with this more kind of open approach that we've had.
Okay. And next question, how do you see the qualification of such software technology against space standards that consider the flight software as highly critical?
Yeah, also another good question. And it kind of in vein with the previous question, it does depend on context for sure. How exactly you need to qualify the software that you're flying, and I've never gone through a full qualification battery, so there's a little bit of maybe inexperience speaking here, but I think that it kind of depends on the requirements that are applicable to your project, and what exact steps you need to take through there. And I don't think it's necessarily black or white. I don't think it's necessarily full Python open source software startup way of thinking, or fully qualified standard flight software thinking. I think there is a little bit of gray space between the two. I don't know if I fully answered your question, but I think that thinking about gradations of qualification is kind of a helpful framework for that.
Okay, and we have time for just one more question. So how many satellites can you afford to lose to gain the advantages of moving faster?
Yeah, very good question. Hopefully not many. So obviously I can't answer in too much detail with a question like that. I don't want to get into financials, but I think what I'd say to that is that we're trying to make it to where we don't actually lose a satellite with this approach, separating out the GNC software as our kind of smart payload app from the core functionality of the spacecraft. I think means that we don't have to worry about it being one of the core solved problems, if you will, that causes a spacecraft to break itself. And so we're focusing our effort on making sure that the GNC software does what we need it to do. And obviously there's things we can do with our ConOps to avoid extra sticky situations, but we think that this allows us to maximize our attention on where we need it, and reducing risk where it needs to be reduced.
Okay, and we're out of time. Thank you so much, Kit.